right, so now we're going to look at 7.2, which is looking at describing simple harmonic motion. And so in this scenario, we are given a graph of position versus time. And we're going to use this information to essentially create graphs for all the other intervals. And so the first thing is to kind of look at the slope of each of these instances. And so if you look at this first part right here, I know that I am in equilibrium. And if you look at the slope of this part, I'm going in the positive direction. Because I'm going in the positive direction, that means I am moving, so I have velocity in the positive, which means I have a positive velocity. So whatever that number ends up being, I know I'm going to start up here. The next stage is looking at point A. Well, point A, the slope, if you were to draw the tangent line, is flat. Well, slope of 0 means that my velocity is now at 0. And this makes sense for thinking about its position because when it's in the equilibrium position, it's moving this direction. And it's going to move that direction, slow down until it comes to rest at that maximum before it turns around to go the other direction. And so then, when we go to part B here, we now have a slope that is going negative. So, just like before, we're going to have a velocity that goes negative. And then at C, our slope is flat again, so we're back to 0. And at D, we're up in the positive, so now we should be back up here. Now, since the graphs are curved and it's going to gradually change, we're not going to have a linear relationship here, that we're going to have the same kind of curve. And we end up getting kind of this cosine graph that looks like this. Now, for the next part, we're going to do exactly the same thing, and that's going to help us find what the acceleration is. The slope of the velocity time graph is going to give you the acceleration. So just like before, we're going to look at the slope of each of those situations. We start with a slope of 0, so we're 0 acceleration. Then we have a negative slope, which means we should go down, 0, positive, and then back to 0. And just like before, it is still having that curve to it, so we are having a nonlinear relationship, which just so happens to be another sine or cosine graph, just depending on how you're looking at it. This one would kind of be like a negative sine graph. Now, sine and cosine are really the same kind of function. They're just shifted over one direction or another. We'll get to that in just a second. While we're here, I'm going to go ahead and do our energy graphs as well. And the thing to remember about energy graphs is that we are only dealing with positive amounts of energy. So we have total energy. You could also have mechanical energy here. That would be the same thing because you're looking at the total amount of stored potential and kinetic. Now, kinetic energy is going to be tied to its velocity. So when you have a lot of velocity, you have a lot of kinetic energy. So if you look at this situation right here, at the start, at 0, we have a bunch of velocity, which means that all of that energy, we're going as fast as we can. So the max energy is going to be in its kinetic. Then we go to a point where it has 0 energy. 0 speed. That means it has 0 kinetic energy, so it's back down here. Then when we go to the next part, we are looking at negative velocity. Well, it doesn't matter the direction. If you have a negative velocity, you have a speed. It's still maximum, which means you're going to have a kinetic energy. Again, we have no negative, so it's back in the positive. And this continues over and over like this. We're talking about stored potential energy. When it is at its maximum, so if you're looking at the graph over here, when you're at some amplitude, you're at its maximum displacement, that means that the energy is not moving but stored in the spring. So when it's at one of the amplitudes, A or C, it's going to have the maximum amount of stored energy in the spring. So those two parts have all the energy. Now, if you're thinking about these two, we know that the total energy is constant. That is not going to change. And it's going to be the sum of your stored energy plus your kinetic energy. And so really, we're just trying to balance the scales. So at the beginning, at time equals 0, we have all kinetic energy, which means we have no stored elastic. And this continues, so forth. Now, this can also be gravitational. It doesn't matter what kind of energy. We're just dealing with a stored energy here. Now, to kind of finish our graphs, what we want to do is we want to create a line here. And you'll notice that with both of these energies, it still does form kind of a sine wave. It's just shifted up. And with your potential energy, it is exactly the same thing. So we got no sharp edges. It is going to gradually increase and decrease just like that. Now, to write an equation for this, there's a couple of ways you can do it. But to find the position, and this is looking at a position in simple harmonic motion as a function of time, there's a couple of ways to write it. The most general form looks like this. X is equal to A times the cosine of omega times t, where X is going to be its position. You can often write this as a function like this. This would be a function, kind of like f of x, a function of time. So if you see that, that means the same thing. You're not multiplying by time here. It's just writing it in that f of x notation. A is going to be your amplitude. Omega, or W as some call it, is the angular frequency or angular velocity. And then t, this is our variable that is going to be changing. This is our time. Now, the reason that this is the case is actually because it's all related to circles. Now, if you have a circle and you're looking at that spring or pendulum or whatever it is that's oscillating, it's going to be going back and forth along that line. So this way, back and forth. Well, instead of writing it as just in the x direction, you can also write it as a circle. And in the circle, it's going to be keeping a constant speed around the circle. That constant speed can be used to find omega. One of the most common ways to write this is to actually look in to figure out what this is actually doing for us. Because as you're going up to some point on your graph, like this point right here, if you were to write this as a trig function like this, this is going to be the distance away. This is x. Now, as this guy is going back and forth, that is changing. That value is going to get bigger and smaller. But that's where your position is at this point in time. This angle is called the phase shift. So you can use theta, but theta often gets confused with the actual angle that it's currently at with your angular velocity. And so this is used to show kind of where it starts. So if we're writing this out, and we're going to use one last thing here, this distance right here. This is the amplitude. The reason it's the amplitude is because just like with the unit circle, it is the same value all the way around. It's 1 unit or whatever that's going to be. So the distance from here to here is your amplitude, which is the same as any point that you pick along your circle. All right, so here's our graph. Now, if I do the cosine of my angle, this is equal to the adjacent, which is x, over the hypotenuse, which is a. The reason I'm picking cosine is because that's the function that uses those two parts of my triangle. Now, I can rearrange this to solve for x by just multiplying by a. So I have a times the cosine of the angle. Now, this value for theta, or this value for phi, can actually be changed a little bit, because we know that omega is the change in your angle divided by the change in time. And if you want to multiply both sides by time, that's going to be what your angle is. So we're just going to take this value right here and we're going to plug that in to our cosine function. So really this tells us that x is equal to the amplitude times the cosine of omega times the time. Now, oftentimes you will see it written out a couple of different ways. So like I said, you can see it in function notation, f of x, or x of t, because it's a function of time. This is equal to the amplitude times the cosine of omega t. Now, one other thing you often see here is they add whatever that initial phase is at. So because this is really the change in your velocity, or the change in your angle, if you add on this phase shift, then that will say, okay, whatever your final angle is at, that's where you're looking. So this is called a phase shift angle. And it just kind of makes your numbers work. It doesn't really affect it too much, but that lets you start at either the equilibrium position or anywhere along that amplitude. The next thing that we're looking at, or another way to write this, is using the sine function. They are really the same, it just means it's starting in a different place. So if you see x of t, or again, either x, it's either are you writing it in function notation or not, and you have the amplitude times the sine, it works exactly the same way. They are indeed the same functions. So this guy, sine function, we know starts at equilibrium. So if you're using this one, we know it's going to start at the equilibrium position. Using cosine means it's going to start away from that equilibrium position, which is typically what you see if you take like a spring. You're going to stretch it to a max amplitude first before you release it. Regardless, they do give you the same functions. So if you wanted to write out the graph for this position versus time, you can use the amplitude. That's going to be how far away. That's so if this had been 5, you would put a 5 in here, times the cosine of whatever the angular velocity is times t. And that would write out the equation for you. All right, so let's do your test for understanding here. Suppose that a vibrating object can be described by the position time function as following. So this right here. So this equation is typically written out for you. You just have to apply it. So we have x is equal to 0.32 times the sine of 7.31 t. Again, it's a function of time, which is why that t is there. This right here is telling us that this is our amplitude, that's our max displacement, and this is omega. Those are the two pieces of information that you have to be able to figure out. Now, x is in meters, t is in seconds, which means all of our units are the same. We do know the mass of the object is 6.2 kilograms, and we want to find the spring constant, k equals question mark. So we know that the period of a spring is capital T. And from our derivation, we know that capital T is equal to 2 pi times the square root of m divided by k, mass over spring constant. That's going to tie my spring constant in pretty nicely. Now, I also know that omega is going to be 2 pi over the period. 2 pi because that is one rotation over the time it takes to complete one rotation, which is the period. I can actually rearrange this for t by multiplying by t and dividing by omega. So I have t is really equal to 2 pi divided by omega. Now that's helpful because I have two values that are equal to t, this one and this one. So I'm going to set those two equal to each other because I know that t is equal to t. So I'm going to say that 2 pi times the square root of m over k is equal to 2 pi divided by omega. Now, we're going to keep simplifying here. We have 2 pi on both sides, so I can actually divide by 2 pi. So I now have the square root of m over k is equal to 1 over w. If I square both sides, that would give me m over k is equal to 1 over omega squared. And now I'm just going to simplify by solving for k. So I'm going to multiply both sides by k to get that out of the denominator. And then I'm going to multiply by omega squared to get that out of its denominator. So the spring constant is really equal to omega squared times the mass. Now that I have that derived, all I have to do is plug in my information from above. So I know that omega is equal to 7.31. So I'm just going to plug that in, 7.31 quantity squared times the mass. And I was told the mass is 6.2. And doing that, that lets me figure out what the K value is, which ends up being 331.3 newtons per meter. All right. The next thing says, give me 3 equations that are going to express the total energy of an object experiencing simple harmonic motion. So, like I said, typically you're using some sort of gravitational or elastic energy. Typically it's elastic because typically you're using springs. And so 3 equations. We have kind of different areas where we know information. So the first area is when you're at an endpoint. When you're at an endpoint, all of the energy is stored. And so the total energy of your system is going to be that stored elastic potential energy. So it's all equal to 1/2 times the spring constant times x squared. But x is really the amplitude because it's at its maximum place. So when you're at the endpoint, x is equal to a. So really, the best way to write this is to say that the total energy is equal to 1/2 k times the amplitude squared. The second location is when it's at equilibrium. This means that there is no net force on it. The spring is not being stretched. It's at a point where the net forces are balanced or 0. And so because of that, we are at, instead of x equals a, we're at x equals 0. We're at that 0 point. So this means that all the energy is not stored but kinetic. So the total energy is equal to 1/2 mv squared. But this is really not just any velocity, it's the max velocity. So I'm going to say v max. And there's one more total energy equation that we can create, and that is if it is between the endpoint in equilibrium. So anywhere else. That means we're going to have some kinetic energy and some stored gravitational or stored kinetic. So again, we're going to use, stored elastic. We're going to be using the elastic potential energy equation here. So the total energy is going to be some kinetic. So we have our 1/2 mv squared. This time we don't have to say V max. It's going to be the velocity at whatever location we are at. Plus, we have the elastic potential energy, which is 1/2 kx squared. Again, this time we're not going to use A because that x is going to be dependent on wherever we are. Those are our 3 equations for total energy. Next part says, how can the equations for the maximum speed of an oscillating object be derived from the conservation of energy? So essentially what we're doing is we're looking for the max velocity. Well, I know that the total energy of the system is the same. These are the same in all 3 of these situations. We could set any of these equal to each other. Obviously, the easiest one here would be to set these two the same, equal to each other, because again, max energy is not going to change. So if we do that, we can say that the energy, 1/2 k amplitude squared, when it's at an endpoint, is equal to the amount of energy at the equilibrium, 1/2 mv max squared. Now, all we have to do is simplify. We have 1/2 on both sides, so that can go away. We are looking for that velocity max. So we're just simplifying this. So we're going to divide both sides by m. So we have k times the amplitude squared divided by m is equal to the velocity max squared. Now, if you take the square root of both sides, we know that the velocity, or the max velocity, is equal to the square root of k a squared over m. Well, the a I can just pull out to the front if I so choose, and I have the amplitude times the square root of k divided by m. That is my equation for the max velocity. Now, if you want to keep working with this equation, we can actually keep going, because just from the previous part, we learned that your kinetic energy, your spring constant, is going to be equal to omega squared times the mass. So knowing that the spring constant is equal to omega squared times the mass, we can actually plug that in over here and get a different type of equation. So let's do that. V max is equal to the amplitude times the square root of, we're going to replace k with omega squared times m divided by m. Well, masses go away, so we have the max velocity is equal to the amplitude times the square root of omega squared. Well, that goes away. So we have that the max velocity is equal to the amplitude times omega. Good habit to make sure you're reminding yourself to label your variables. So A is going to be the amplitude. It is a position in meters. K is going to be the spring constant. Which is in newtons per meter. M is the mass in kilograms. And omega is the angular velocity, which is in radians per second. Both of these are totally good equations to use. This one is typically used the most often. I want you to see the relationship here between simple harmonic motion and uniform circular motion. In UCM, we know that the velocity is equal to the radius times omega. V is our omega. In simple harmonic motion, we have the max velocity is equal to the amplitude times omega. Do you see how these are the same thing? Because the radius of your circle is quite literally the amplitude. It's the farthest it can go. Since that is the case, these are exactly the same thing, which means I can also say that omega is going to be the max velocity divided by the amplitude. All right, the next part here says show the equation for the maximum acceleration of an oscillating object as derived from Newton's second law. We know Newton's second law is good old F net. The net force is equal to mass times acceleration. When we have this oscillating object on a spring that can go some amplitude like this, the acceleration is at a maximum when the force is greatest. Well, the force is greatest when it's past that equilibrium position. It's at the maximum where it wants to have the strong force going this direction. So A max is at x equals A. All right. Net force wise, the net force acting on this object is the elastic force. And we know from Hooke's law that the elastic force is equal to the spring constant times the displacement, F equals kx. We don't have to include direction here because we are including the direction and looking at the net force. That part is not mattering, so we can just look at the magnitude of it. All right, so if we replace that information right here, we're just going to replace that in for our F net. We know that the spring constant times the position is equal to mass times acceleration. Now, if I want to make it at its maximum, again, we know that it's at its maximum when x is equal to the amplitude. So oftentimes you will just write it as k times the amplitude is equal to mass times the max acceleration. Again, make sure you are watching your capitals and lower cases. Spring constant is a lowercase k. I know that kinetic energy is a capital K. Oftentimes people will write kinetic energy KE instead, just so it doesn't get confused. Capital A is for amplitude, lowercase a is for acceleration. All right, so if we rearrange this then the max acceleration is equal to k times the amplitude divided by m. Now, keeping all this information, we've got a lot of different things that we can do here. We know that the spring constant, if I want to get rid of that spring constant again, I know that it's still omega squared times the mass. So I could write this out again and say that the max acceleration is omega squared times m times the amplitude divided by the mass. Those end up canceling, which tells me that the max acceleration is omega squared times the amplitude. So the equations that we can use here is that the max acceleration is equal to omega squared times the amplitude. Or we can also say, if we use that omega squared, we convert that down using this, omega squared is going to be the max velocity squared divided by the amplitude squared. So if we use that information, we can also say that the max acceleration is equal to the max velocity squared. And then it would be times the amplitude divided by amplitude squared. So that simplifies to be just divided by the amplitude. Which, if you look at our UCM equations, Again, you're going to see a lot of parallel here. Uniform circular motion equations, the centripetal acceleration was v squared over r. Well, and we also said that it was equal to omega squared times the radius. In simple harmonic motion, it is exactly the same thing, where the max amplitude, the max acceleration, is equal to the max velocity squared divided by, instead of radius, we have amplitude again, which is also equal to omega squared times the amplitude. Really, all you have to realize is that the radius is equal to the amplitude. That's the difference. Everything else is exactly the same. All right, we'll stop here for now. Go ahead and look at this and start looking at what would the period be, what would the frequency be. Think about the equations because this is going to be applying those equations.